Well, hello everyone, and my apologies for not being there with you in person. I hope those of you who were at the workshop last week had a very productive time, and I'm looking forward to telling you about the DSA 2000. So I'm Vikram Ravi. I'm a professor of astronomy at Caltech. I'm speaking to you from Los Angeles, and yeah, I'm going to tell you about this project that we think is really going to change the way radio astronomy is done in the coming years, and hopefully you'll see why. So the DSA 2000, first of all, is going to consist of 1650 6.15 meter antennas. So this is equivalent in collecting area to a 250 meter dish. For those who have been following this project for a few years, at one point we were planning on 2005 meters, but we've optimized for both sensitivity while maintaining survey speed to get this somewhat increased collecting area with fewer dishes. This gives us at zenith the same sensitivity as fast. The array will be sited in a valley in Nevada, and we'll basically see the whole sky north of a deck of minus 38 degrees, with interferometric PSF of about 2.7 arc seconds in the middle of the band. So DSA 2000 is not just a fast transient telescope, although fast transients are a major part of what we do. Within this 0.7 to 2 gigahertz band, it will always be imaging. It'll always make images of the sky, both in the continuum as well as on spectral lines, with full polarization, and providing the capability to detect slow transients. But it will also simultaneously search for both fast transients as well as pulsars. It will also be able to time a few pulsars within the beam at any given time as well. All data will be public. This is a condition of our funding, and they'll be made available in an archive with no proprietary period. We expect to be starting our major surveys in 2029. So if you sort of follow things like the SKA, and maybe some of you have been to the GMRT or other radio telescopes, you'll know that the site is really important. It's important to have a radio quiet site with an excellent RFI environment and an excellent sort of soil conditions, and in some cases atmospheric conditions as well. And we think we've found the best site, certainly in the continental United States, for this. Permitting on the site is underway, and we expect to start construction late next year. This place has some very interesting sort of bits of history. One of the nearby highways is called the Highway to the Extraterrestrials, because this happens to be, not near, but not all that far either from Area 51 in Nevada as well. So the telescope will conduct surveys over 5 years, over a 5-year prime mission. And in doing so, it will spend about 65% of its time on this cadenced all-sky survey. This will be sort of revisiting patches of the sky over and over and over again. It'll spend something like 10% of its time on gravitational wave follow-up in deep fields. This is following up neutron star mergers, for example, detected by ground-based gravitational wave detectors, hopefully LIGO India, by the time this thing comes online, as well as spending about 25% of its time on pulsar timing array science. So this is timing millisecond pulsars to search for signatures of gravitational waves. This is an approximate breakdown and may well evolve, but this is the plan as it stands. So to put this in context, the 2020s really is the decade of surveys. It's sort of a decade where all around the world, telescopes are being built that will really kind of revolutionize the way that we don't just see individual objects in the sky, but the whole astronomical sky. So you'll all be familiar with at least some instruments on this slide, like the Rubin Observatory is coming online now, and the optical. The Euclid Space Telescope is already taking observations. We hope that Roman will be launched in a year or two. And there are a few others as well. And DSA-2000 really fits into this kind of context pretty neatly. We really think that we're the radio equivalent of Rubin. At one of our early reviews, Matthew Bales, I think, told us that he thought that the DSA-2000 can keep all radio astronomers worldwide busy for a decade. We hope that that is the case. Oh, there we go. And I just want to emphasize again that the data that we produce will be public with no proprietary period. This includes science-ready datasets, both in the continuum and spectral lines and polarization, with photometry at kind of every sort of detected source in the sky, together with SEDs, light curve fits. We expect to be also making sort of metadata such as alerts and so on public for pulsar and FRB detections as well. And the public archive that we produce is under development by Schmidt Sciences, who have so far been our primary funders. This is the philanthropic arm of Eric and Wendy Schmidt, Eric Schmidt being the former Google CEO. We will also, as part of the project, maintain a commissioning and science verification archive to kind of enable us to bring the thing online. So why are we doing this? The science case that we have is pretty broad, and to give you a sense, within these sort of four themes, for example, in multi-messenger astronomy, we're going to be following up the mergers of neutron stars to detect the radio afterglows, as well as directly detecting gravitational waves via pulsar timing. Our H1 observations will provide detailed information on galaxy kinematics, gas contents, and so on. For example, the THINGS survey, which for several decades led the field with the VLA, we will do that, but improve it by a factor of a few hundred, just in galaxy counts. In terms of the dark sector and strong gravity, we expect to have various probes of cosmology, such as being a very competitive strong lens finder for time delay cosmography. We also expect, via the discovery of many pulsars, to be able to find relativistic binaries to test theories of gravity. And then in the dynamic radio sky, we expect to find many FRBs and many slow transients. For example, our detection forecast is something like 10 to the 5 FRBs over the course of the survey, each localized to better than half an arc second, together with 20,000 new pulsars and 10 to the 6 slow transients. This few to a few tens of individual GW sources we predict via pulsar timing array science. This is all enabled by the very high survey speed of the array. This is a somewhat outdated plot. The latest estimate pushes this a little bit to the right to be equivalent to SKA mid. To emphasize some of the science goals, our FRB science goal is really focused on the idea of determining the distribution of matter around and in between galaxies with FRBs. So, for example, with this large sample of FRBs, we expect to be able to place incredibly accurate constraints on the effects of feedback during the process of galaxy formation on the baryon distribution. This is a major uncertainty in using relatively small scales for cosmological purposes, for example, from galaxy redshift surveys or from weak lensing studies. Indeed, when we combine our data with Euclid weak lensing data, we expect to be able to improve constraints on the sum of the neutrino masses. I'll emphasize that the fact that neutrinos even have mass is probably one of our clearest signatures of physics beyond the standard model. And so we're very excited with what we can do with a large FRB sample here. On the pulsar side, we expect to detect many new pulsars, but we'll have a real focus on finding relativistic systems to enable us to test theories of gravity across a whole range of gravitational potentials and curvatures. Just for completeness, via pulsar timing, we expect to localize a few tens of individual sources within the stochastic gravitational wave background. Evidence for the background has been presented by several pulsar timing arrays, and when we come online, we will be the major telescope worldwide for pulsar timing array science. A good way to think about it is that, in fact, our motivation at the very start of the project was really to replicate kind of Arecibo and or fast sensitivity, but be fully steerable, and dedicate significant time per year to pulsar timing science. So the data products sort of are pretty detailed in their nature, but one thing to really emphasize here is that, again, we're not just an imaging telescope, we also do fast transients. We're not just an FRB telescope, we also do imaging. All these data products are created all the time and commensally, meaning they're all made together. The images will be science ready in the sense that they should look like optical images of the sky. And this is really enabled by a few things, including the fact that we have a lot of antennas, as well as a back end that we call the radio camera. The commensal pulsar and FRB search is enabled by a back end we call the chronoscope, and there will also be a pulsar timing back end. So moving on now into kind of where the status of the kind of design is at the moment. I'm going to present some kind of refinements we've made to the design in the past year, but in doing so, I hope to also just give you a sense of what we're actually planning to do overall and highlight some of the key technologies. So one thing that we've realized is that it's likely more efficient to implement a variable depth and cadence survey rather than simply covering kind of all the visible sky with fixed observing time and a fixed number of epochs. So one concept for such a variable depth and cadence survey is shown here, where we end up having, over 5 years, 7 epochs in basically the northern Euclid sky, as well as the galactic plane and bulge, and then something like 4 epochs in the region of the sky where we're most sensitive, this is close to zenith, and then a reducing number of epochs as we go away from zenith. And so the logic here is that we want to reach the source confusion limit in our stacked images efficiently. And once we reach that, we don't really want to integrate further, because for much of the extragalactic transient science, it doesn't really matter where you look, right? That's not true, of course, for the galaxy. So for the galaxy, we're interested in galactic transients. We're also interested in doing this commensal pulsar survey, which requires not just discovery, but also follow-up timing. And so we expect to do that via a dedicated extra number of epochs on the plane and the bulge. Another design refinement is the, let me just pause this one sec, is the way that we've optimized the configuration and infrastructure. So our array configuration looks something like this. Now, why is there this little sort of spike there and this strange cutout here? Well, this is the boundary of the site that we have. And so there's some really amazing work by Josh Albert in Leiden and collaborators to try and find a way to take sort of idealized configurations made by Dave Woody here in the Owens Valley, and then adapt them to the site that we have, as well as all the various constraints on the site, like sensitive plants and areas where animals might make their homes, sensitive cultural artifacts, and so on. Try to adapt the configuration to be minimally impactful on all these site features while maximizing both the PSF fidelity, meaning reducing the side lobes, and also sharpening up the main lobe of the PSF as much as possible. And so this optimization was done, and it results in a PSF that has sort of remarkable mid and far side lobes relative to what we do if we did something sort of more naive than this extensive optimization. You might find it fun to scan the QR code and take a look at our ArcGIS collaboration site. This sort of shows via various layers locations of antennas and so on. I'm not sure if it's up at the moment actually, but please feel free to try it out. The other thing that we've done is we've kind of figured out how to best place all the infrastructure pieces. So the idea is that on site, we really will have very little hardware. This is one concept of what it might look like, where on site, this building is used to stage the antenna construction, and then it disappears when antenna construction is done. And we're left then with just a few buildings, a few up there for maintenance, and then a couple of basically shipping containers that host the digitizers and channelizers and the networking hardware to put the data onto backhaul fiber. And so it's a really very lightweight site at that point. Let's see, there, can I fit through? There we go. And then the rest of the what we call the radio camera and the chronoscope will be implemented on compute hardware about 110 kilometers away in a nearby town. The radio camera is really a concept that's also pretty unique to this telescope. Typical interferometers like the VLA or the GMRT have images that really require visibility-based deconvolution to create the images with high fidelity. What the large number of antennas together with our calibration scheme enables is a deterministic stream processing pipeline that directly creates images. To give you a sense of how the number of antennas makes a big difference, you can kind of see here just what our project scientist Fabian Walter would look like when sampled with different arrays, and sort of with no post-processing done, no clean, for example. And you can see that when you get to 2000 antennas, in this case, artifacts, at least visually looking on the screen like this, basically disappear. And so, of course, quantifying what it means for artifacts to disappear depends on your model for the sky as well. And so there's a significant forward modeling effort based on real sky models, calibration errors, the PSF, errors in the sort of beam shapes and so on, that we're using to try and quantify just what errors we can tolerate given the science we want to do on the real sky. For example, if we want to reach a confusion limit in some percentage of the sky, what errors are tolerable? Now, the chronoscope is, as I said before, the back end that we use to detect FRBs and pulsars. And so this is kind of it's big. The idea is that we want to use about a quarter of the band to search for pulsars and FRBs in real time. It has to be done in real time because, like with the radio camera, where we can't really store the visibilities due to the enormous data volumes, here we also can't really store the search mode data because of enormous data volumes. We expect to do real-time commensal sort of searches for dispersed pulses in 6 million beams that tile the field of view. Now, this sounds like a lot, but just for context, this is about 3 to 6 times that of what the VLA real-fast system searches, and something like twice that of what ASCAP Krakow searches. So not really very far away from existing systems, because of course, when you think in the image plane, a beam is a pixel. And if you're doing image plane searches, you're searching a lot of pixels, right? And you can say that you searched 6 million beams. The key difference between what we're doing and what instruments like ASCAP and the VLA do is that we cannot dedisperse the visibilities and have a much smaller problem than if we dedispersed the pixel data. It's kind of equivalent because we have a lot of visibilities as well. So it just becomes a giant brute force compute problem in many cases. If we can solve this, we expect to see sort of 10 to 20,000 FRB detections per year. And these will come with public alerts. We also expect to be performing near real-time commensal searches for pulsars in the 0.1 millisecond data. This will include targeted searches towards continuum sources from our own surveys, as well as blind searches in a limited number of beams at a given time. The pipelines that we're putting together are expected to be fairly standard, nothing too unusual here. I don't need to dwell on this too much at this point. Let me also say that one reason why we are able to achieve the sort of sensitivity that we expect at moderately low cost is the innovations that have been made in the antenna and receiver design. The antenna has to be extremely highly performant in a few different ways. To make the radio camera work, we need surface accuracies that is something like lambda over 200, meaning RMSs of better than 1 millimeter on the surface, which is, strange for a telescope operating at 20 centimeters wavelength. Equivalently, we also need the pointing accuracy to be better than an arc minute, which also places constraints on gravitational deformation, how well the feed is located, manufacturing QA, and so on. We also need to minimize ground pickup and crosstalk, for which purpose we have this shield around each reflector. This is similar to what Arecibo installed. And then the other thing is that a real bit of kind of magic in our process is the fact that we're also able to achieve receiver noise temperatures that are basically as good as cryogenically cooled systems, but at ambient temperature. And so this is now being demonstrated. It's achieved by a combination of really excellent transistors, as well as a well-designed input matching network. And the resulting sort of prediction is a TSIS divided by aperture efficiency of sort of, better than 30 Kelvin within a few tens of degrees of zenith. This is TSIS divided by efficiency, not just TSIS. We're beginning to validate some of this at a test array in the Owens Valley. These are still 5-meter dishes. The 6.15 meter dishes are currently being built in Germany. We're also testing in the Spring Valley site, the site that we're hoping to begin construction on next year. This is just a reflector placed in the back of a truck. We drove to a particular private property there. Early measurements of TSIS are very promising. I'll point out that the particular spectrum analyzer used here has a very bad resolution bandwidth, which means that these RFI signals, which largely originate in space, kind of leak well across the band. But you can see that in the good parts, we're getting 20 Kelvin on Sky, which is gratifying. One thing I want to really point out before finishing is that in the last sort of 4 to 5 months, we've really become aware of and are now fully targeting the use of these new rack-scale compute hardware systems from NVIDIA. AMD also has an equivalent. We really think that these are revolutionary for large radio astronomy arrays. Our current plan targets about 6 exaflop of processing at FP8, which can be done in just 5 racks with a power cap of well under a megawatt, something like 600 to 700 kilowatts, which is absolutely incredible. These racks are basically sold as racks. They're not sold as individual sort of cards or even individual server units that can be plugged in. The vendors sell racks that are fully integrated. For example, all the GPUs in the racks are connected via sort of proprietary data links that effectively enable them to act like one big GPU, where all the memory in the entire rack is addressable from anywhere, both on the CPUs and on the GPUs. And so we're currently benchmarking the implementation of sort of the key parts of the radio camera and chronoscope pipelines on this sort of hardware. The initial results are very, very promising. So yeah, this really, we think, it brings the really ambitious kind of goals. For example, the chronoscope of doing these searches in 6 million beams, in other words, with full sensitivity and full field of view for FRBs. With this sort of hardware, we really think that it's very achievable. Just to finish up, so when we're fully operational in 2029, we expect that this will be the most powerful gigahertz frequency telescope worldwide. The key sort of technologies that make this possible are the radio camera and chronoscope developments on this new hardware and the highly performant antenna and receivers. We're also exploring a complementary low-band system to accompany this, to make use of the same infrastructure, where in that case, the main science goal would, of course, be EOR science. With the dishes, we expect to do transformational science and multi-master astronomy, cosmic history, dark sector and strong gravity, and the dynamic radio sky. We anticipate a very rich yield of fast transients, and all the data that we produce will be served publicly with no proprietary period. And yeah, leave it there and happy to take questions.
Thanks, Ravi. Very interesting indeed to learn about the DSA-2000. Questions from the audience? Meanwhile, those online, if you have questions, please type your questions on the chat window and I'll come back to you.
Hi, I'm Yash. So I have a question, like since the disk array are very compact, will there be shadowing effect for low elevation sources, or are they sparse enough to?
The array is not so compact. The configuration, let me just focus on this for 1 second. The dimensions of the site are something like 19 by 15 kilometers. So we're only placing 1650 dishes in that area. The typical spacing is a few hundred meters between antennas. That said, we do have some short spacings as well, where shadowing will be an effect. But the number of baselines, for example, under 50 meters is in the sort of several tens, and that's all.
Let's thank Vikram again and move on to the next speaker. Thanks, Vikram, a lot. Thanks a lot.
Thank you. Thanks.